Good day, everyone. Our topic for today is about curvature and refraction, elevation determination. So, what is curvature and refraction? Earth curvature and atmospheric refraction are two primary systematic errors that must be taken into account when measurement becomes sufficiently long. Curvature and refraction affect any measurements dependent on an optical line of sight or energy wave, which is quite a few. Due to curvature, the points appear to be lower than they actually are, while due to refraction, they appear to be higher than they actually are. The effect of curvature being greater than that of the refraction, the combined effect causes the points to appear to be lower than they actually are. Okay, so to understand well what is a curvature and a refraction, let's discuss them one by one. So curvature, Earth has a curved face which is assumed to be a level surface, but the line of sight as furnished by the leveling instrument is horizontal and not the level line. Therefore, all points on the line of sight are not equidistant from the surface of the Earth, and consequently, the points read on the staff are not strictly at the same level as horizontal hair of the diagram. The level line falls away from the horizontal line of sight, and the vertical distance between the horizontal line and the level line denotes the effect of curvature of the Earth. Okay, let's have this figure. The figure shows a typical plane surveying situation. The direction of the gravity at the instrument at one end and target at the other are parallel. To keep things simple, let's assume that the instrument and the target are at the same height above a horizontal reference surface, and the line of sight between them is also horizontal. The zenith angle Z at the instrument is 90 degrees. As distances get longer, directions of gravity begin to converge, which makes the reference surface curve. The single horizontal black line between instrument and target in the figure separates into three different lines. The red line is the original line of sight at the 90-degree zenith angle. It is perpendicular to gravity at the instrument location. The green line is the new line of sight between the instrument and the target. It is perpendicular to the gravity only at its midpoint. And the blue line is at a constant height above the reference surface and perpendicular to the gravity along its entire length, making it a curve. Angle A is the zenith angle change due to the curvature, and distance C is the vertical distance caused by the curvature. Although the Earth is a complex surface, we can approximate it with a constant radius spheroid. That works fine unless we're doing global measurements, but that's beyond the scope of the material here. What we want is reasonable math to deal with the gray area between the plane and the geodetic surveying. So to determine the value of angle A and the distance C, we're going to use two equations. First, the equation 1, which is the equation needed, or the equation to be used in order to find the angle A. So the equation is A is equals to sine raised to negative 1 times D over 2R. Then equation 2, which is used to solve the distance C. So equation 2 is equals to C is equals to D squared over 2 times R times cosine of 2 alpha or 2A. So D is a straight line distance from the instrument to target, which is it is a measured distance between the instrument and the target, while R is the earth radius, which is 20,906,000 feet, or 6,372,200 meter. So in most of the surveying textbook, it gives equation 3 for the vertical distance curvature error C. It is an approximation for the equation 2 and doesn't require computing the angle A. So the third equation is C is equals to 0.239 times F squared, which is equals to 0.667 M squared. So that is our equation 3, where F is the distance in thousands of feet. For example, for 2000 feet, our F is going to be equals to 2. Then M is the distance in thousands of meters. How significant are the curvature, angle, and the vertical errors? Well, this table shows the results of the equations 1 and 2 at increasing distances. As you can see, the distance is increasing from 100 to 5,000. And the values of A in seconds and C in feet are also given with respect to the increasing distances. As we have observed, up to about 500 feet, neither A or C are very large, but they become significant at the longer distances. Next, let's discuss the refraction. It is a well-established law of physics that rays of light passing through layers of different densities do not remain straight but are refracted or bent down towards the denser medium. Let's look at the given figure. As you can see, the ray of light from the staff to the instrument is not straight, but it follows a curved path AD concave towards the earth, as the near the surface of the earth is denser than the upper layers of air. Atmosphere has density, and a electromagnetic energy ray passing through it will be bent. That includes the line of sight through an instrument's telescope. The denser the atmosphere, the more the line of sight is bent. Atmosphere is generally densest near the ground and decreases with elevation. When sighting longer distances, our line of sight starts at the instrument's density condition and passes through the progressively denser atmosphere towards the target, bending downward. The amount the line of sight refracts from the straight line is not linear. At 200 feet, it is not twice the refraction at 100 feet. Over short distances, the atmosphere density distribution is relatively uniform. At longer distances, that is probably not true. Solar heating and weather fronts can cause anomalous atmospheric pockets, disrupting the otherwise smoothly refracted path. Local heat waves, even over short distances, can randomly affect line of sight displacements. Basically, getting a strong handle on how refraction behaves is relatively difficult. To simplify the situation somewhat, its overall effect on readings is relatively small, considerably smaller than curvature. In most computations, refraction error is taken as a percentage of Earth curvature. It varies from 17% at sea level, which is dense atmosphere, to 7% in mountainous areas, less dense, with 14% used as a common overall factor. It's computed using equation 4. Because line of sight is depressed, the equation is negative. So our equation 4 is equals to r is equals to negative 0.0033 times f squared, which is equals to negative 0.093 m squared, where d is a straight line distance from instrument to target, which is a measured distance, and r is the earth radius, which is 20,906,000 feet, or equals to 6,372,200 meters. The table shows the refraction displacement at select distances from 100 to 5,000 feet. So, as you have observed, from 400 feet, the following values for our R is negative